Welcome to Maths with EJD. In this video, I'll be taking the second part of the blending and mixing problems with linear programming. In the other video, I had talked about animal feed mixing problem, how to get the kind of nutrients and all of that you require in mixing feed for animal. So here I'll be talking about blending. It's blending and mixing problem. So we are talking about blending of crude oil. So um, imagine that a refinery, a refinery blends two types of crude oil. So like you have crude A and crude B. The objective, the objective is to mix these crude oils to create a refined product with a required API gravity, the required API gravity. Okay. Um, so in that case, so with the required API gravity, right? While minimizing the cost of the raw materials. Okay. So imagine that you have crude A. Crude A is $20 per barrel. And then the API gravity, API gravity is 30 degrees. Then you have crude B. You have crude B, which is $30 per barrel. $30 per barrel. And then the API gravity is 35 degrees. All right. So then we have specifications. We have refining specifications. Refining specifications. So the first one is that the refined product, a refined product must have an API gravity of at least 32 degrees. That's one of the constraints. The other one is that the total amount of crude oil used must be exactly 100,000 barrels. Okay. So let's imagine that the decision variables are A, that is amount of crude A, amount of crude A in barrels, amount of crude A used, and small b is amount of crude B used, amount of crude B used, that is the number of barrels of crude B used. Crude B in barrels used. Okay, so if that is the case, we can then have the problem statement or problem representation, as you like, problem representation. So then we can say we are minimizing. So we say minimize, want to minimize the cost, which we can say is C. So the first one costs $20 per barrel. Okay, $20 per barrel for the first and $30 per barrel for the second. So the cost we are minimizing will be 20A plus 30B. That's the cost we are minimizing. Then the next thing now we have the constraint. So subject to what's the first constraint? So we want to make sure that, you know, if we get, of course, A is the amount of crude A, right? And B is the amount of crude B. And so that simply means that, let's say, now, since the API gravity, the first specification is about the API gravity that has to be less than 32 degrees. So since the API gravity for the first for crude A is 30 degrees and the API gravity for crude B is 35 degrees. So it means that if we say 30 degrees multiplied by A, the amount of crude A, and 30 degrees multiplied by the number of barrels of crude B rather, and then we have to divide that by the sum of crude A, number of barrels of crude A and crude B. So in that case now, so that is subject to um 30, that is subject to 30 degrees times the number of barrels plus 35 degrees and the number of 30 degrees times the number of barrels of crude A plus 35 degrees and the number of barrels of crude B, all divided by the total number of barrels of crude A and crude B. And by the time we do that, that has to be greater than or equal to 32. That's the requirement that we need at least gravity of at least 32 degrees. So it has to be greater than or equal to 32 degrees. That's the first constraint. Now, from all indications, you can see that this is not a linear. We are talking about linear programming, but this constraint is not in any way linear. Okay. So that is we are going to look at that by the time we solve the problem. Then the second constraint is saying that the total amount of crude oil used must be exactly 100,000 barrels. That means we cannot exceed, if you sum up A and B, you cannot exceed 100,000 barrels. So it means that A plus B has to be exactly 100,000 barrels. Okay. And of course, we have A and B being greater than or equal to 0. So what are the components like? uh this is the objective function, objective function, and that is basically the cost which we want to minimize. And then we have the gravity constraint, gravity okay, API gravity constraint rather. Okay, do that better. API gravity, API gravity constraint. And then this is can I just say barrel constraint? Barrel constraint. Uh, say crude oil barrel constraints. Barrel constraints. Okay. And then lastly, we have the non-negativity constraint because we cannot have negative value of barrels. Non-negativity constraints. Okay. So that's all we have. Now the next thing is to solve, right? Of course, our go-to place is Python for solving. Of course, you can use Excel, there are many other tools, MATLAB and everything, but I just love to use Python. So mostly I'll use linprog and PuLP. So let's go for that. So I minimize this a bit and then I go for this crude oil blending problem with linear programming. So using PuLP now, okay, let me just restart this, clear cells. Okay. View now. I want to put the line numbers. Yeah. So in the first case I used PuLP. Now there's a little bit of trick here because what we have actually is technically non-linear, but of course we can divide through, right? You can multiply through by x plus y. If you look at this now, so we can say 30a plus 35b is greater than or equal to 32. So we can say that's 30a plus 35b is greater than or equal to 32 into a plus b. So we have something like that happening right over here. So we define the problem as in 12, then we have all the necessary constraints and all that. And then we just do this. Now, for PuLP, right? PuLP is telling us that we need 60,000 barrels of crude A and 40,000 barrels of crude B. Whereas for linprog, well, and of course, the minimum cost in that case is $2,400,000, right? For that. But when you use linprog, see what we're getting. So linprog is telling us that we need 100,000. So it means we should just focus on the whole, we should get all the crude from crude A. We should get all the only crude A, 100,000 barrels of crude A, and that will lead us to $200,000. Now, of course, if we compare the values, right, we need minimum cost. So linprog is giving us a value less than what PuLP is giving. Normally, they should give us the same thing, but probably because of the non-linear that gravity case, which is technically non-linear, right? So I guess I present you the two, right? But I'll go for the less one, the one that gives the cost that is smaller. That is $2 million. So get 100,000 barrels of crude A, and in that case you spend $2 million, as opposed to the $2.4 million you spend, as we see for PuLP, where you do 60/40. So I'll just focus on linprog. So using scipy dot optimize dot linprog, we have A is 100,000. So all the 100,000 barrels should come from crude A, and then B is 0. And that is going to give us a cost of, that will give us a cost of C, which is $2 million. $2 million. Okay. This means that the minimum costs, okay, let me even see the objective function. Objective function is 20A. So we are taking A to be 100,000 barrels, right? So 100,000 times 20, that is, yeah, 2 million. Yep. So this means that the minimum costs possible is $2 million, and that is only possible if 100,000 barrels of crude A are used. As such, crude B is not necessary. Crude B is not necessary for the blending. Okay, and that's how that goes. So if you have not subscribed to this channel, be sure to do that right away and hit the notification bell so you can always get notified each time a new video is released. And don't forget to comment so that I can know if you want me to teach a topic or solve a problem. And also like and share so that more people can have access to this great content. Till I come your way again, keep optimizing. Bye.